This lecture will focus on partial derivatives. Partial derivatives are the natural expansion of derivatives to functions of two or more variables. In many ways, when you get to partial derivatives, everything that you've learned about derivatives up until this point remains completely true. The only thing that changes is the idea that when you take a derivative, you're always taking it with respect to some particular variable. And when you do an optimization problem, you're going to have to optimize it with respect to both variables. So in order to take a derivative of a function f of x, y, we need to specify whether we're talking about the derivative with respect to x or the derivative with respect to y. So I'll start off by taking the derivative here with respect to x. So I'm taking the derivative of the function with respect to x. Notice the change in notation. I've switched from using a print d to using a script d in front for this operator, ddx. When I'm taking the derivative with respect to x, what I do is I treat x as a variable, and I treat my other variable as a constant. And you'll see what I mean by that as I work through this. So I look at the first term. I'm going to take the derivative using the power rule. I bring down the 3. I'm left with x squared. Now, as I look at this second term, and I want you to be really careful. This is completely different than the implicit differentiation things that we did last week. Here, for a partial derivative, y is just a normal old constant. It's like the number 5, or the letter a. So I'm going to, because it's multiplied by the variable, leave it out front unchanged, just like you would a constant. And then I'll take the derivative of x squared, and I get 2x for that. Now, as I come to this last term, I do not have any x's in the term, and so this is a constant whose derivative is going to be 0. So I'll rewrite that just to move the coefficient 2 on the second term out front. And I'm done taking the derivative with respect to x. However, I'm not done taking all of the derivatives because this function is also a function in terms of y. So I'm going to take now the derivative with respect to y. And the process here is exactly the same as what I did before, except now with respect to y instead of with respect to x. So now I'm going to treat the x terms like constants. This first term is a constant when I'm taking the derivative with respect to y, so its derivative is 0. In the second term, I will treat the x squared just like a constant, like a 5 multiplied in front of the y cubed, and then I'll take the derivative with respect to y of y cubed. I use the power rule and get 3y squared. I look at the third term. I leave my constant out front. I use the power rule to take the derivative, and I'm done. I can rewrite that just to make it a little bit cleaner, but at this point, I'm done. You can leave it like that. You can factor out 3y squared if you would like. They're the same expressions. All right, so let's do another example. So again, we'll take the partial derivatives with respect to x and with respect to y. So I take df dx. I'm treating x as my variable and y as my constant. The first term is a constant, so of course its derivative is 0. For the second term, I take the derivative with respect to x, as I usually do. For the third term, I do not have any x's in this term, so it is also treated like a constant, and I'm left with 2x. I now take the derivative with respect to y. Again, the first term is 4, its derivative is 0. The second term, does not have any y's in it, so this is just like a constant by itself. Its derivative is also 0. And then I use the power rule to take the derivative of the first term. I realized I forgot a negative sign on that first one, and here I also have a negative for y. So here are 2 more examples. Why don't you pause the video right now and go ahead and attempt them on your own, and then we'll come back and I'll walk you through them. All right, so I'll take the partial derivative here with respect to x. I'm treating y as a constant, so that y to the 5th power just stays out front because it is multiplied by an x, but it's just like a number that's sitting there. I take the derivative of the x term, I get 3x squared. I can move my constant out front, and I'm done. I take the derivative with respect to y now. Now we're treating the x cubed as a constant that just stays out front as I take the rest of the derivative. I use the power rule on the y term. I get 5y to the 4th, and I rewrite it just for clarity. And I'm done. This second example is a little more complicated because you do have to use the chain rule here. So I'm now going to start off taking the derivative with respect to x, and notice here that we have a function 2x plus 3y inside of another function, so I will use the chain rule. I'm going to rewrite this function like this with the fractional power, with the 1/2 power there, just to remind myself of what I'm doing. So I use the chain rule. I bring down the 1/2. I leave my inside function unchanged. I subtract 1 from the power. And now I need to multiply this by the derivative with respect to x. I take the derivative of the 2x term. I get 2. I take the derivative of the 3y term with respect to x. We're treating y as a constant, so its derivative is 0. So that's just a 2 multiplied out front. My 1/2 and my 2 cancel each other out, and I'm left with 1 over the square root of 2x plus 3y. The partial derivative with respect to y is very much the same process. I bring down the 1/2, I leave the inside term unchanged. I subtract 1 from the power. I take the derivative of the inside term, and now we're doing it with respect to y. So the derivative of the first term is 0, and the derivative of the second term is 3. So now I'm left with 3/2 times the square root of 2x plus 3y in the denominator. Here are 2 more examples for you to practice on, and then we'll come back if you want to pause the video right now. All right, so I'm going to take the derivative of this first expression with respect to x. I get df dx. This first term is just in terms of x, so I take the derivative as normal. I get 6x. The second term has a y in it. I treat the y as a constant. The derivative of the x is 1. So I am left with my constant y squared. I take this next term. I am treating the y as a constant, so I just worry about taking the derivative with respect to x. I get 2x, and my constant sticks around. I have 2xy. And then the derivative of this last term, y, is 0 because we're treating the y as a constant. I'll do the same thing now with respect to y. My first term, there are no y's in it, so it's just a constant whose derivative is 0. My second term, I'm treating the x as a constant, so I bring the 2 from the y squared down. X remains as a constant times y to the first power. I do the same thing with the second term. Now the derivative of y is 1, so I'm left with just this constant x squared. And then the derivative of y again is 1, so I'm left with a minus 1. For the second expression, I'm going to take first the derivative with respect to x. The derivative of x here is 1. I'm treating anything with a y in it like a constant. So my e to the y is just a constant that's multiplied by 1. And my y term here goes away because its derivative is 0 because we are taking the derivative with respect to x and treating y as a constant. If I now take the derivative with respect to y, I'm treating my x as a constant, so it's going to stay out front. The derivative of e to the y is simply e to the y, so that term sticks around. And then the derivative of y is 1. The other useful thing about this process of partial derivatives is that it does not just apply to functions of two variables. You can actually use it on functions of any number of variables. So let's start off with just this simple function, x, y, z. And I'm going to take all three partial derivatives. There will be as many partial derivatives as there are variables in the function. So if I take dg dx, I'm taking the derivative with respect to x and leaving my y's and z's as constants. So the derivative of x is 1 times y times z because y and z are just constants. My derivative with respect to y, the derivative of y is 1. I'm treating x and z as constants, so I have just x times z. I take the derivative with respect to z. You notice the pattern here. The derivative of z is 1, and I'm left with x times y. So now we're going to take all three partials for this function h. I take the partial derivative with respect to x. In this first term, I treat my y as a constant. I bring down the 2. I'm left with 2x times y, the constant. There are no x's in my other two terms, so I'm done. I take the derivative with respect to y. In this first term, I treat my x squared as a constant, and the derivative of y is 1, so I'm done. In the second term, the derivative of y is 1, and so I'm left with my constant z. There is no y in the third term, so I'm finished. And now I take the derivative with respect to z. There's no z in the first term, so its derivative is 0. The derivative of the second term, the derivative of z is 1, so I'm left with the constant y minus 2z. And those are all three partial derivatives. So here we have a slightly more complicated function. I'm going to take all three partial derivatives. I take df dx. Now here I have two terms multiplied together, so I'm going to have to use the product rule. I have this natural log of y sitting here that's going to just be a constant. So when I take the partial with respect to x, I'm just going to pull out the ln y because I know that it's a constant that's just going to stick around through the full process. So now I need to take the derivative of this term x e to the xz. Well, I'm going to use the product rule. The derivative of the first is 1, so I have 1 times e to the xz unchanged, plus x unchanged, and I need to take the derivative of e to the xz. And sometimes at this point, I find it helpful to just over on the side, just write out what would the derivative with respect to x of e to the xz be. Well, z is just a constant, so I'm going to use the chain rule. The derivative of e to the x is e to the x, so I have e to the xz unchanged, and the derivative of xz, where z is a constant, is just z. So coming back to the problem that I was working on, I have this x that I was left with because it's the constant, or sorry, because it's the product rule, and I have the first term unchanged times the derivative of the second term. So it would be x times z times e to the x z. And I'm done with that partial. If I want to, I could factor out an e to the xz term, and then I would have e to the xz ln y times 1 plus xz. That's the kind of simplification that is not required, but helpful if you happen to see it, because it leaves a slightly more interpretable version of the expression. I now take the derivative with respect to y. So notice that everything out front here is simply a constant. So I just have to worry about the derivative of the natural log of y, which is 1 over y. So I leave my terms from out front as constants divided by y. And I'm done. I take the derivative with respect to z. Notice that only one of the terms has a z, so my x and my ln y will be constants out front, and then I just need to take the derivative with respect to z of e to the xz. It's the same basic pattern as I had here, except that now I'm taking the derivative with respect to z. So if I need to take the derivative with respect to z of e to the xz, it's a chain rule. I have e to the xz, the derivative of the outside function evaluated at the inside, times the derivative with respect to z of the inside function. The derivative of xz is just x. So I have x e to the xz. That is something you should simplify just because you have 2x squared, or sorry, you have 2x's multiplied together, and your final form of the expression should look something like this. You could also write it like this just to be clear that the e to the xz is not inside of the ln y.